Hey guys, welcome to the Ace Your IB Math Exams in 10 Weeks Challenge. It's Bruno, the IB Math teacher. Over the last few years, I had the privilege of teaching HL Math in one of the most prestigious IB schools in Brazil, and I've also worked as an IB examiner. And for this May 2026 cohort, I've decided to release a 10-week challenge specifically designed to help AA IB Math students to be better prepared for their upcoming IB Math exams. The idea behind it is that you sharpen your skills with a weekly exercise list composed of 5 different questions, one from each topic: number and algebra, functions, trig, probability and statistics, and then calculus. All of them IB style, all of them demanding. You can download the PDF, the exercise list, with the link in the description of this video, completely free, and follow along as we go through the exercises together. I would also encourage you to share this YouTube video and also the exercise list with your colleagues so you can study together, given that studying together is much more fun than studying by ourselves. So let's get to it. Let's get through week number 1 of the Ace Your IB Math Exams in 10 Weeks Challenge. So what we have in front of us is the following. Use the principle of mathematical induction to show that 3 to the n is greater than n plus 1 squared for all natural numbers greater than or equal to 3. Now there's quite a large number of induction proofs videos in this channel and in the website if you want to dive deep into it. And this is a very specific case, one that involves inequalities, as I was mentioning. It has a recipe behind it with 5 steps. We're going to go through all of these 5 steps, starting with step number 1, which is to write the propositional function. The propositional function is nothing more and nothing less than copying what the exercise has given you. This is what you need to prove. And by the way, don't forget to write the interval as well. Step number 2 is the base case. And to tackle the base case, you start with the first integer that was given to you in this interval. So in this case, n has to be equal to 3. We're going to test the base case for n equals 3. The left-hand side of this inequality is 3 cubed, which is 27. And the right-hand side is 3 plus 1 squared, which is 16. And indeed, the left-hand side is greater than the right-hand side. Therefore, you're going to write this, the base case holds. Step number 3, the inductive hypothesis, P of k. You're going to rewrite your P of n, but replacing n by k. And you're going to assume that this is true for some, and then you rewrite the interval, which means in this case, natural numbers greater than or equal to 3. So this is our assumption. Step number 4, which is the hardest step in any induction proof, which is the inductive step. For inequalities specifically, we write P of k plus 1 by replacing the k's by k plus 1, which in this case means 3 to the k plus 1 has to be greater than k plus 1 squared, which of course is the same thing as this. Now, we didn't prove anything just yet. We did score a few marks in the beginning, but the majority of the marks are right here. And the way that we solve induction proofs with inequalities is by starting with P of k and manipulating it so we get to P of k plus 1. So starting with P of k, which is what we're assuming to be true, we know that 3 to the k is greater than k plus 1 squared. And then we need to ask ourselves, how do we go from here to here? And there's a nice little diagram that I like to use in order to explain what needs to be done in the next few steps. And by the way, you shouldn't write this in the exam. This is just me explaining the process. Now, if you say that something is greater than something else, or in this case, greater than or equal to something else, and we take the smallest side and we make it even smaller, meaning we can represent this by little squares, we go from 2 to 1, the inequality stays the same, meaning we don't flip the inequality, we don't break the inequality. By the same token, if we take the largest side, the biggest side, and we make it even bigger, well, we don't break the inequality as well. It's still consistent. And obviously, if we multiply the whole inequality by a positive number, it doesn't break as well. Why am I saying that? Because in order to go from here to here, which by the way is our goal, one of the things that we can do is to multiply both sides by 3, which doesn't change the inequality. And in this way, or by doing so, we get our 3 to the k plus 1 already on the left-hand side, which is a good thing. We're getting closer to the goal. But we still need to take care of what shows up on the right-hand side to make it exactly the same as the right-hand side of p of k, meaning we need to get here to k plus 2 squared. Given that 3 times k plus 1 squared is the same thing as 3k squared plus 6k plus 3, what we got here is 3 to the k plus 1 is greater than 3k squared plus 6k plus 3. Now what we would like to get is k squared plus 4k plus 4, which is of course not the same thing. However, and this is where this diagram comes into play, if we break this 3k squared this way, which by the way doesn't change the expression at all, and if we break this 6k this way, which also does not break or does not change the expression as well, we could replace this 2k squared by 0. And why can we do that? Well, we're talking about the smallest side. If we make it even smaller, the inequality stays, it remains. And we get one step closer to the goal, which is this, by the way. And the next substitution that we can do or can make is to replace this 2k by 1. Why would we do that? Well, first of all, so we could get a 4 on the right-hand side. But the thing is, this is possible because k is a number greater than or equal to 3. Now substituting 2 times k, which is at least 2 times 3, which is 6, by 1, which is smaller than 6, it's fine because we're talking about the smallest side. And there we have it. We just got to our goal, which is 3 to the k plus 1 has to be or is greater than k squared plus 4k plus 4, which by the way is the same thing as k plus 2 squared. And the only thing that we still need to do is to write the conclusion. So step number 5, the conclusion. Given that p of 3 is true and p of k plus 1 is true whenever p of k is true for some positive natural number greater than or equal to 3, then by the principle of mathematical induction, p of n is true for all natural numbers greater than or equal to 3. And that's it. All right, so for exercise number 2, we have a polynomials question. We have a cubic with coefficients a, b, c, and d respectively, and the 3 roots are r1, r2, r3. And it is given to us S1, or at least it was labeled S1, the sum of the roots, which we know, by the way, all along that it's negative b over a, given that we know how to find the sum of the roots in a polynomial. It was also given or labeled S2, the product of the roots 2 by 2, which is c over a. And now S3, which is the product of the roots, is negative d over a, which we knew also all along that it's negative 1 cubed. So in this case, negative 1 times the constant, which is in our case d, over the coefficient, which multiplies x cubed, which is a. So negative d over a. If our function f of x is this, and the roots are alpha, beta, and gamma, then we know that their sum is negative b over a, which is 8. We also know that their product is equal to negative d over a, meaning negative 1. By the way, a, b, c, and d are the coefficients of this cubic. So 2 down, 1 more to go. We just need to evaluate alpha beta plus beta gamma plus gamma alpha. And that is c over a, which in our case means 9 over 1, which is equal to 9. So exercise A is done. Now, how could we find the sum of the roots squared? We could start with the expansion of this raised to the second power, meaning alpha plus beta plus gamma times itself, which if you FOIL, you get alpha squared plus beta squared plus gamma squared plus 2 alpha beta plus 2 beta gamma plus 2 alpha gamma. And these last 3 terms can be written as 2 times, and you probably notice already the pattern, alpha beta plus beta gamma plus alpha gamma, which is exactly what we calculated lastly in the last step. So we know this is equal to 9. We also know, and color coding this, that this is equal to 8. Therefore, we have 64 equals alpha squared plus beta squared plus gamma squared plus 2 times 9. Therefore, the sum of these roots squared, it is equal to 46. Now, B down, let's get to C. Question C. The way to get these terms is to square alpha beta plus alpha gamma plus beta gamma. If you do so, and let me copy this to a different page, you should get alpha beta squared plus alpha gamma squared plus beta gamma squared in a very similar way compared to the last exercise to question B. And then plus 2 alpha squared beta gamma plus 2 alpha beta squared gamma plus 2 alpha beta gamma squared, which you could rewrite as the following. If you factor out over here a 2 alpha beta gamma, what you get is 2 alpha beta gamma times alpha plus beta plus gamma. And do notice that we have the product of the roots, which is -1. We have the sum, which is +8. We have this product, which is 9, and this is what we want. Therefore, alpha beta squared plus alpha gamma squared plus beta gamma squared is equal to 9 squared, which is 81, minus 2 times -1 times +8, which is equal to 97. Now lastly, question D. If we're trying to create a cubic polynomial which has roots alpha squared plus beta squared plus gamma squared, that means that the sum of the roots, which by the way is -b over a, is equal to whatever we got for question B, which is 46. We also know that the product, which is -d over a, which by the way is the same as alpha times beta times gamma squared, this is equal to -1 squared, meaning 1. And we also know that C over a, which is the product of the roots 2 by 2, is exactly what we got for question C, therefore 97. Now we have these three equations here. And if you choose A to be 1, and you can make that choice, because it doesn't matter what you choose for A, the other coefficients are going to change proportionally. If we choose A to be 1, we get B equals -46, D equal to -1, and C equal to 97. Therefore, for this new cubic polynomial, we have A as 1, -46 as B, 97 as C, and -1 as D. In exercise number 3, we have a trig identity to solve, which is not a very complicated one. There's just one caveat here, which is the fact that the arc inside the cosine or off the cosine is not theta but 2 theta. That means that we're going to search for the solutions whenever we get to the last step of this equation, not within the interval from 0 to 2 pi. We actually have to double it. We go from 0 to 4 pi in this case, and that's because we have 2 theta in our cosine. So given that we want our solution to be in between 0 and 2 pi, and due to the fact that the arc is 2 theta, towards the end of this equation, we're going to search for the solutions in between 0 and 4 pi. And that's not going to be a problem because in the end, we're going to divide everything by 2 again, so our range of values will be in between 0 and 2 pi. All right, so what do we have here? 4 cosine squared of 2 theta is equal to 3, which means that cosine squared of 2 theta is 3 over 4. Cos of 2 theta is equal to positive and negative root 3 over 2. Don't forget about the positive and negative. And by remembering the unit circle, we have our solutions over here, over here, over here, and also over here. Given that all of these points, they represent the cosine comma the sine of these angles, we can see root 3 over 2 and negative root 3 over 2 in all these 4 cases. And in addition to that, we need to look for the solutions, as I was mentioning before, not from 0 to 2 pi, but from 0 to 4 pi, which means that we need to go around once more. If these solutions are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6, when we go around once more, we're going to have pi over 6 plus 2 pi over here, which is 13 pi over 6. Then also over here, 5 pi over 6 plus 2 pi, which is 17 pi over 6, then 19 pi over 6, and 23 pi over 6. And by the way, I don't know what this 2 is doing here, but this is 11 pi over 6. Now, remember that these are the solutions for 2 theta, given that we were looking for the arcs, which would give us root 3 over 2 as the cosine, or negative root 3 over 2, within 0 to 4 pi. Now let's list all these possibilities over here. And knowing that these are the solutions for 2 theta, the possible values of theta are, we divide everything by 2, pi over 12, 5 pi over 12, and so on and so forth. So these are all the solutions for theta. On exercise number 4, we have a probability question, one that involves conditional probability, the given that types of exercises in probability. And we notice the given that because of this notation. In this case, P of B given not A and P of A given B. And the best approach for this exercise here is to use both the formula for the conditional probability, but also a Venn diagram whenever we get a chance to use it. We know that P of A given B is P of A and B over P of B. So this formula is in the formula booklet, which means that this 0.5 represents the probability of B and not A over the probability of not A. And the 3 over 11 represents the probability of A and B over the probability of B. Now, a little harder to spot. However, given that the probability of A is 0.2, we know for a fact that the probability of not A, which is the complement of A, is 1 minus 0.2. So in this case, 0.8. Now notice that we can use it here and find our probability of B and not A as 0.5 times 0.8, also known as 0.4. And if we call the probability of A and B X, we can represent through a Venn diagram P of A and B over here, P of B and not A over here. Also, knowing that P of A is 0.2, this probability is 0.2, therefore this is 0.2 minus X, X being the intersection between A and B, and P of B, which can be seen here, is equal to 0.4 plus X. Now we have everything that we need to finish this equation, to finish solving this equation. So we have 3 over 11 equal to X over 0.4 plus X. If you cross multiply, you get 1.2 plus 3X equals 11X, which means that 8X is equal to 1.2. Therefore, X, which is the probability of A and B, it is equal to 0.15. And we're not done just yet. We need to find P of B given A, which is probability of B and A, which, by the way, is the same as the probability of A and B, over the probability of A, which is 0.2. Now, probability of A and B is 0.15, so we get 0.15 over 0.2, also known as 0.75. And there you have it, exercise number 4.